Give me a sec. Okay. Um, Today we're going to talk about the last lecture modules called Input and Modeling. Actually, it's in our lecture module 15 over here. And the slide is over here. And you can see the slide. And also there's the software come with it for the class suggested by the textbook. Okay, so fairly straightforward. Okay, right here. So the software called Easy Fit. One of your questions and in term projects stated you have so many data available for this term projects, but some of you want to figure it out what are the inter-arrival time for the order or the lead time for each one of the material and consumption of each order, like order amount. We've been exercising those so far in our homework and exam by just giving you the number. But in real world, actually, these are not readily available, this distribution. How can we, using the raw data, and convert it into an estimated distribution, either for your inter-arrival time, processing time, lead time for your materials, or other order amount, basically. We give it to you. So let's take a look at this sections. I have the PowerPoint presentation over here. Let's do that. All right. And also the in the textbook, okay, if you open it, it's in the Appendix A portion of the textbook, and you should be able to look at it. Okay, it's in the appendix section. This section actually tells you most of the stuff in CMIL book, and they referring the Easy Fit is the software they're using. So here I'm going to using the textbook directly and just showing you in the textbook. In the real world, we do data collection, and a lot of IE hire to production line or facilities or service facility, and to do data collection. A lot of time they refer as a time study. Time study basically collect the information, inter-arrival time, processing time, patient arrival patterns, and so on and so forth. And the main things for we talked about input analysis is we have followed three major steps. Of course, the first step is collecting data and put into a spreadsheet. A second, and the second step is basically using the so-called identifying the candidate distribution. Okay, the candidate distribution usually refer as you study the distribution or the histogram of your data or the distribution of your data and trying to guess, oh, my data looks like normal distribution, exponential distribution, Erlang distribution, beta distribution, so on and so forth. I hope you still remember some of those distributions from your Step 510 classes. And for each one of the candidate distribution, you attempt to estimate the parameters for these candidate distribution. For example, normal distribution, they have two major parameters. Okay, one is called a mean, and the other one is called standard deviation. And For example, for exponential distribution, you should probably have only one parameter, which is the mean. We call the mean arrival time or average arrival time. And for exponential distribution, we all know the standard deviation is equals to the mean. Okay, exactly. And trying to estimate those parameters for with each one of the candidate distribution, because your data, if you study the histogram, for example, like that, we will have more example in our PowerPoint presentation. For example, this is your data, and this could look like a beta distribution, could look like a Erlang distribution, could also look like a beta distribution. And some of the Weber distribution with a certain parameter also looks like that. So for those candidate distribution, for each one of them, we estimate their parameter and compare the candidate distribution with the histogram. Then we compare the candidate distribution function against your data, and this portion we'll call the goodness of fit process. I'm not sure you got this type of topic, covered this type of topic in step 510 or step 511, either one of them. And based on the so-called goodness of a fit, and you choose the best representation of your input, and using that as the distribution function you put into your simul program. So today's lecture, we're going to basically follow this chapter, Appendix A, but we focus on the theorem and the rationale of that. And finally, we're going to show you how to using a software called Easy Fit and trying to fit that data. Okay. So for our simulation so far, you probably experienced two types of input. One called a deterministic, which is yes. No. Thank you for reminding me. And this is okay. You got it? All right. Okay. So far we have a so-called deterministic type of input, either number of units for resources, or called a resource capacity, and entity transfer time could be a fixed time if you put an entity on a conveyor or automatic transportation machine. And inter-arrival time and processing time could be deterministic for some fixed production line. However, majority of our input inter-arrival, for example, customer arrival time or processing time, many times are stochastic, which we call a random. So, so far in our assignment, we give you input follow exponential distribution with a mean of 12, and processing time follow per distribution with between 2 to 5 minutes, most likely 4 minutes, and so on and so forth. Okay, so and like I said, and so far we're taking a shortcut, just giving you those information for your homework assignment. So far, have you concentrate only on the the modeling portion of the simulation. However, the data collection in a real world is a very time-consuming process, and this is also a costly process. We have sent a senior design team member for the entire summer sit into the hospital lobby and trying to collect the inter-arrival time for patient, the different type of patient, different different departments the patient want to go to, what type of treatment or seeking. And for the pharmaceutical pharmacy area, or the clinical area, or the waiting area, and the foot traffic, and so on and so forth. So what we would want to do is we will review the basic statistic process for our data we collected, And for example, the type of randomness, descriptive statistic, mean, standard deviation, and so other part we describe a little bit, talk about a little bit. Now we're going to see how to implement the idea using input modeling using an easy fit software. You can do this in the mini tab, but the easy fit software is free for our student, and then you basically just load the data like a spreadsheet or CSV file or Excel file. You can directly use that as fitting for different distribution. So we're going to create and interpret the empirical distribution function, and so we can talk about those in this lecture. Okay, we're just going to skip some of those. How important the randomness in the real world? For example, manufacturing area, the processing time, operation time, the breakdown, we all simulate that in our homework so far, call interruptions and others. Okay, in the real world, actually, the breakdown is less likely to happen in the manufacturing area. Is what we call the scheduled maintenance. It's considered a breakdown, but it's a scheduled. And this kind of random breakdown could be either triggered by number of parts, the machine process, or could be a period of time. And computers, also computer system, for large computer system, or today we're talking about cloud environment, the inter-arrival time for jobs, okay, and for jobs you using for job types and different type of requirements or different job type for your cloud base. Some of them as is Google for email server, Gmail. Some of them as is Google for storage called Google Drive, and other using photo services, the other ones using map. They're all running on the same cloud, and all different requirement or job types or requests from different user on the web browser command to share the resources in the cloud. Service industry, the most randomness part should be the inter-arrival time for customer. Also depends on the different customer who have a different requirement. The service time or the service type could be also random. Other than that, the server also go on so-called vacation or on the break for the employee or the server. The last item is the military, and military has a lot of usage for randomness in the simulation, arrival time, and the payload of missile or airplane. Actually, when I was in college in the military service, actually my job is trying to come up with a simulation system to simulate the warplane attack of your missile base and how to counter attack or defense your missile base. The outcome of any kind of military engagement, okay, could be random, and sometimes you using a platoon, and actually you can eliminate the entire squad and so on and so forth. Okay, and so one of the goals in our simulation is using the data we collected from before and trying to put into our simulation model and to let the model recreate or mimic the behavior of the real system. So can we just doing three things, okay? Can we just using the data we collect, the raw data we collect, or the data you're getting from your term project, directly feeding your simulation and trying to perform the simulation that way? Of course you can, and you know how to do that already in your term project. All you have to do is import your the data table as which I have YouTube videos specifically tell you how to do that. Or you can input that and then using appointment arrival based on the table, and you just recreate the exact arrival pattern. However, to generalize your model, many times people prefer to using a so-called approximative distribution or possible distribution to put into your data. So in this case, your simulation model using a possible range of distribution or randomness and generate from the historical data, but not using exactly the historical data. Many times we find out using this approach can be generalize your model behavior and figure out the possible outlier in your system, and how to deal with the so-called outlier or exceptional situation in your model. And the third one, you can using the educated guess. In the real world, many times, if you interview the foremen or the operators or the people who work on a job, the frontline person, many times they don't know what type of distribution they have. They usually give you an answer, oh, it's about the customer come here is about 30% as trying to open a new account, and another 40% is trying to make a deposit or withdrawal, and another 30% probably need just do the bank transfer and check the balance and so on and so forth. So they don't have exactly a distribution function to give you, and they only have a rough idea what kind of proportion of different type of service. And also they probably can tell you for open account generally takes about 20 minutes, to make a deposit or withdrawal usually takes about 5 to 10 minutes, and so on and so forth. So the major three step is from your raw data. First, you need to determine what possible type of distribution it could be. For each one of the possible distribution, what could be the best estimated parameter. Many times in your step 510 or 511, we refer this as called a maximum likelihood estimator. Okay, I hope you still remember how to do those. And then we're going to check, are these distribution parameter estimation good enough? So we're going to perform a so-called a goodness of fit calculation, trying to compare for each type of possible distribution, which one give you the best result. Okay, so that's the three major steps we have. Select the possible distribution family, estimate the parameter using the maximum likelihood estimator, and determine how good the distribution fit our data. And this part we call the goodness of fit test. Okay, and also, just like I said, we can use the raw data itself in our simulation directly to replicate, see if this simulation model recreate exactly the same phenomena or behavior of your true system. Or we can using empirical distribution function, this we already know, using random dot discrete function, trying to estimate 10% type 1, 40% type 2, 50% type 3, and so on. Okay, so today we're going to focus on the last part, using your data to fit or approximate by a theoretical distribution function. And first we hypothesize which type of distribution function we have, then estimate their parameter using the maximum likelihood estimator. Finally, we perform a goodness of fit test to see which distribution function will be better for us. Okay. First, in order to determine or estimate what type of possible distribution function our data could be, I will refer you to our Appendix A to our textbook for detail. But here what you're just trying to do is giving you an overview. There are two major types of random variable, discrete and continuous. Discrete data usually means, okay, and the number of or quantity of each order coming with is usually a discrete. So it's a 15, like what we have is 15 plus what random binomial distribution 0.4 of 20, meaning you throw a coin for 25 times, and each time the truth come out, the possibility for truth outcome is 40%. You throw it 25 times, and you add the numbers together and see what type of how many you got. So these are the discrete distribution. A lot of times the inter-arrival time, processing times, the failure rate, and those are continuous random variables. So most frequently we're using our simulation model. Okay, so we're using some of the descriptive statistics. For example, the mean, the median, and the mode. We can see our data, how they look. Okay. If it's perfectly symmetric, it's like a normal distribution, the mean and the mode and the median, they're all the same. If it's tilted to the left, this part skewed to the left, and this type of a distribution we'll call it positively skewed. And basically the mode is going to be less than the median and the, less than the mean. If the data is skewed to the right, and we call it negatively skewed, and the mode actually is going to be greater than the median, and the median was going to be greater than the mean, so on and so forth. Another type of descriptive statistic we call it variability. First, we call it variance and standard deviation. Okay. Second, we call it coefficient correlation. Coefficient correlation is basically using for multivariable. So see how the standard deviation according to the mean, and that's the last one we call the range width. And this range width is a lot of time we're using a triangular distribution or per distribution. And basically you see the data from your you collected. They have a minimum time and a maximum possible time, and there's most likely time, and they will call the range and width. Finally, we have the skewed and the curtices, and basically skewed meaning you tilt it to the right, we call it positive skewed. You tilt it to tilted to the right, we call it negative skewed, and tilted to the left is negatively skewed. Okay. Finally, the kurtosis is the thickness of the distribution, how concentrate your distribution is, and the mean or median value. Here I give you a very simple example, 219 data point, inter-arrival time in terms of minutes, stored in the increasing order. So put it into Excel spreadsheet. I can plot the histogram, okay, and with a different number of bin and more fine grain, you can see that it's not very smooth. If you increase the bin sizes, and the curve becomes more and more skewed. Okay, let me just using a pointer to. So using a more coarse-grained bin size, you see this distribution a little bit more smooth. If you're using too fine-grained bin, and you see this distribution is kind of a zigzag. So, but descriptive statistics, we can know the minimum is 0.01, the maximum is 1.96, mean is about 3.399, it was about 0.4, and so on, and we can see that. And normal distribution give you 500 of those. Actually, I'm using Excel to generate this, using the average of 10, standard deviation of 2, randomly generated, 500 data point. Actually, I can reverse calculate it, numerical calculate it. The mean is about 10.02, and standard deviation is about 1.9. Okay, I can also plot it into a different, in the histogram, it looks like. And I can also approximate these either with a normal, with a 10.2, which is originally used in the pink line, dotted line right here, or I can using log normal. Actually, this time, the log normal actually is better, looks like it's better fit. So many times they're not exactly one. So both of them could be a good estimate of our data. Exponential distribution, I have 500 data point using the average inter-arrival time is 10. So I generate 500 of them and calculate numerically. And I can fit them with this 3 separate distribution. One is gamma distribution with the point A and 10. Second one is exponential distribution. And third one will be Weber distribution. I think looks like they all fit pretty well except the gamma distribution. Okay, so but how we can know which distribution exactly the better. So here's the part we're going to show you how to using the easy fit. I'm going to go really quick. Let me bring up the, you can download from our okay, easy fit, really simple interface, almost like a almost like our mini tab, I would say. Yeah, let me also bring on this. I just generate some example data. Give me a sec. I'll show you two-way of loading that. Very similar to your mini tab. This is the data we call it. I'm using Excel spreadsheet to generate it and called gamma distribution.csv file, and they are actually, let me see, 500 of them. And I can either using cut and paste, copy and paste into this part, and using that to directly, this is we're going to call it table 1, and go on to analyze, called fit distribution. Okay, I'm going to call this column. All right, and I'm assuming it's continues for now, and it will quickly just fit for all the distribution, possible distribution function the software has, okay, and giving you each one of the parameters actually, and you can see that each one of the estimation they give you. This is your histogram, and that the line is the fitting for different distribution. Okay, so this is a visually. You see that some of them are good fit, some of them, and they rank by the best fit they find, and the not very good fit they find also. So you ask me how this, which one I determine what is a good fit, and you can give you a summary of the fit result and give you the number 1. Fitting, they suggest is beta distribution with these parameters, and blurs or Cauchy and chi-square distribution, and so on and so forth. Remember, the original distribution data I generated from Excel is using gamma distribution, but the gamma distribution is ranked number 19 in this case. So actually we can see that from here. The software has the 3 different goodness of fit one was called Kolmogorov-Smirnov test. You probably learned this in Stat 510. And Anderson-Darling and K-square. K-square is mostly using for discrete distribution. Kolmogorov-Smirnov and Anderson-Darling are usually using for continuous random function. So if you click on one of them, the rank, it gives you the rank for each one of the distribution. Okay, and you can actually click on each one based on each criteria. For Kolmogorov-Smirnov, it estimates the gamma distribution is number 1. Anderson also is number 1. K-square estimate is number 4. What is the best one for K-square? So K-square is called a Kolmogorov-Smirnov distribution, which not very good estimation. So you can choose which criteria or goodness of fit algorithm suggests, and looks like this is gamma distribution statistic, and based on the gamma distribution you can figure it out their possible parameter. So, and also the nice things about the chapter appendix, let me okay, this part in page 412, and the table shows you if this is based on the goodness of fit, easy fit. If they give you certain parameter, how do you put in to the C-mill portion? Is that okay? So should be fairly straightforward for you. So for your home term project, you just need to massage your data into this format and you should be able to. Other function like this also, and you can generate your data as well. Here you can random number your data. So number of sample size, if you're going to using exponential distribution, for example, mean of 10, you're going to generate using the current data table. You can using a new data table, and you just generate right away another set of distribution. And then you can test. You just click on the lighting bulb here. It will try to tell you I'm going to using the second column variable 2 to estimate. They give you this. So it's very simple to use, easy to use software, and designated for this purpose only. It's much more straightforward than your Minitab as you using non-parametric analysis. But this software is free for 30 days, all you need for this. And they give you other type of plot as well. They give you the cumulative distribution function plot and the so-called survival function plot, the hazard function plot, the PP plot, see how they deviate from the estimated portion, and the QQ plot is basically similar. All right. Any question for the software so far? Of course. I mean, these are just built in so many different distribution functions. I thought it's easy to use. That's why I introduced it in the class. Also, it's recommended by the textbook. You are welcome to use any type of software you use. Minitab has those, R has those, MATLAB has those as well, and I think Python statistic modeling has those as well. So many of those are public domain, freely available, using any tools you want. I just introduce one of the so-called input modeling for dummy type of software for you, but feel free to using any other software you prefer. Is that okay? This is not the limitation. It's one of the suggestion. Feel free to using Minitab if you want. If you're using Python, that's fine too. Okay. So rest of the presentation, just talking about the detail step. I'm not going to spend time. Again, I already do the live demo here, the software. But in case you still need some guidance, you can follow the slide to do how to use these functions. Any question for me for this lecture?